I am Jay Prakash, working in the Department of Chemistry at Sri Ramakrishna Mission Vidyalaya. Today, we are going to see the various wonders of science. The development of science and technology have produced so many products which are useful to man. Now, suppose you take a product, it has to begin with a starting material, and this material has to be subjected to various operations like cutting, heating, melting, abrading, etc. to attain the product. Now, suppose you want to heat a material to a very high temperature, then the equipment in which the material is subjected to heating should be lined with materials which can withstand that particular temperature, and those materials which can withstand very high temperature without undergoing any change chemically or physically like melting, these are known as refractories. You can define refractories as those materials which can withstand very high temperature without softening or undergoing any change. Now, what are the uses of these refractories? Actually, these refractories are used where very high temperatures are needed for a particular operation, like construction of furnaces. In furnaces, the temperature is very high, like about say around 1000 degrees, and in kilns, converters, crucibles, etc. So the inner part of these furnaces, etc., are lined with materials which can withstand the temperature, and these are known as refractories. And these are also used in the manufacture of cement, glass, paper, metals, etc. Now, coming to the characteristics of refractories, the first character they should possess is that they should be infusible at the operating temperature. Suppose you have got a material which has to be heated to 1000 degrees centigrade, then at that particular temperature these should not melt or they shouldn't be infusible. Second property is refractories should be chemically inert, that is, they should not go under any change at the particular temperature, and there will be so many gases and molten metals, etc., at the particular temperature, and they should not also react with those products. Then the third property is that they should resist the abrading action of gases, flames, etc. The fourth property refractories should have is that they should not crack or lose size at the operating temperatures. Next, they should expand and contract uniformly. When a material is subjected to heat, it will expand, and when the temperature is brought down, it will contract. But this expansion and contraction should be uniform, otherwise the material will crack. Next property is that they should withstand overlying loads, or at very high temperatures they should be able to bear loads, that is they should have mechanical strength. Next, we go to the classification of refractories. Refractories can be classified based on their chemical nature or chemical properties into three groups. One, acidic; second, basic; and the third is neutral refractories. Acidic refractories are acidic in nature. They are not attacked by any acidic materials, but they will be easily attacked by basic materials. Example, silica and alumina. The second class is the basic refractories. Basic refractories are basic in nature and they are not attacked by any basic substances or basic chemicals. Next, examples are magnesite and dolomite, but these will be easily attacked by acidic materials. Coming to neutral refractories, these are prepared from weakly acidic and weakly basic materials, and they are neutral in nature. Example, graphite. Graphite is basically carbon and carborundum. So these two are examples of neutral refractories. Neutral refractories are not attacked by basic or acidic materials. Refractories can be classified into 4 groups based on their refractoriness. Refractoriness means the ability to withstand the temperature. Now, first class is low heat duty refractories. They have PCE value from 19 to 28. We'll see what is PCE value later on. And the temperature at which these can be used is 1520 to 1630. Next, intermediate heat duty refractories. These have PCE value from 28 to 30, and the refractoriness or the temperature at which this could be used is 1630 to 1670. Example, fire clay bricks. Next, high heat duty refractoriness. These are PCE value from 30 to 33, and refractoriness range from 1670 to 1730. Example, chromite bricks. And last is superheat duty refractories. These have values PCE more than 33, and the refractoriness is above 1730. Example, magnesite bricks. Regarding the properties of refractories, the first property a refractory should possess is refractoriness. What is refractoriness? It is the ability to withstand very high temperature without softening or undergoing any change in shape. That is, it should not undergo any deformation. Now, the refractoriness will vary from one material to another. So, this refractoriness has to be measured, and then only we can say how far it is a good refractory. They don't have sharp melting points because these are prepared from inorganic compounds, and usually they are a mixture of compounds, and hence they don't have sharp melting points, but on increasing the temperature they soften. So at a particular temperature, when they soften, the temperature is taken as a softening temperature, and this softening temperature is expressed in terms of a number known as PCE, that is pyrometric cone equivalent. Now, this PCE is a number representing the softening temperature of the material of 3 mm height and 19 mm triangular base. We will see some of the values for some refractories. Silica bricks have PCE value 32. 32 means immediately they will understand that is the value of the softening temperatures 1710 degrees centigrade. Then alumina bricks, they have PCE value ranging from 36 to 38. That is, the softening temperature is in the range 1800 to 1850 degrees centigrade. Then magnesite bricks have PCE value 38. Pyrometric cone equivalent test is carried out for 4 reasons. 1. To determine the softening temperature of a test refractory material. Second, to classify the refractory, to which class it belongs to. Then, third, to determine the purity of a particular sample. If it contains any impurities, that will affect the softening temperature. Hence, this test is useful to determine the purity of the material. Then, it is also useful to determine whether the material can be used at a particular servicing temperature, whether it will suit our temperature conditions of servicing or not. Next, we come to the measurement of this PCE. How we can carry out this PCE? That is, the material of interest is taken and the softening temperature is determined, and it is compared with what we call as Seeger cones or pyrometric cones. These cones are having softening temperature which is already known. They have got a standard combustion and also well-known softening temperature. The PC values are determined by taking the refractory material and converting it into a pyramidal cone, and along with this pyrometric cone, that is materials whose PC values are already known, are taken, and all these are kept in an electric furnace, and the furnace is heated steadily at a heating rate of 10 degrees centigrade per minute. So with rise in temperature, the temperature of the cones will also rise. At one particular temperature, the test cone will start softening. When it starts softening, the apex will start bending and will keep on bending, and it will finally touch the base. The temperature at which the apex of the cone touches the base is taken as the softening temperature. And the softening temperature is not expressed in terms of degree centigrade, but in terms of what we already saw, that is PCE values. The Seeger cone or pyrometric cone, which matches with the softening temperature of this material under test, its value is fixed as this PCE value. A good refractory should have good high refractoriness. Higher the value, better is the refractory. The second property of refractoriness of refractories is refractoriness under load, which is in short known as RUL. But this is related to the strength of the material. Refractories, especially those which are used in metallurgical operations, should bear varying loads. That is, the loads will change at high operating temperatures, and this should not in any way affect the refractories. So these should have very good mechanical strength. Only when they have very high mechanical strength, they will be able to withstand the varying loads. In general, the softening temperature decreases with increase of temperature. So this load bearing capacity of a refractory can be determined by RUL test. That is, the specimen under test is made into a shape of base 5 centimeters square and height 75 centimeters, and a weight of 3.5 or 1.75 kilograms per centimeter square is applied, and next the specimen is heated at a steady rate of 10 degrees centigrade per minute, and as the temperature keeps on increasing, it will start taking up the temperature heat, and at the temperature at which the deformation of the specimen takes place by 10% is taken as the refractoriness under load, that is RUL. Higher the value, greater the refractoriness under load, better will be the quality of the refractory. The third property of refractories is porosity. That is, when you take a material, there will be very minute holes called as pores. Now these pores can alter the properties of a refractory. Now it is defined as the ratio of pore volume to bulk volume, and it is given by the formula porosity P is equal to W minus D divided by W minus A into 100, where W is the weight of the specimen saturated with water, and then the weight is taken in air. D is the weight of the dry specimen, and A is the weight of the specimen saturated with water, and the weight is taken in water. This is another important property of a refractory, because it can alter the chemical stability, strength, abrasion resistance of a material. So this is very, very important, like other properties. When a refractory is having high porosity, there are certain advantages and also some disadvantages. First we'll see the disadvantages of high porosity refractories. If they are highly porous, then the strength is reduced, or they have got a very poor strength. Second, this high porosity reduces the refractory resistance to abrasion, or can easily get abraded, and it also reduces resistance to corrosion, or they can get easily corroded, that is, they can be affected by the environment. So these are the three disadvantages of high porosity refractories. There are also two advantages of high porosity refractories. That is, these materials have got low thermal conductivity, because there are a lot of air spaces in between the materials, and this air is a very poor conductor of heat. Hence, this conductivity is very poor, and hence these can act as very good insulator, and this property has been utilized for forming lining in furnaces and ovens. The second property, or the second advantage, is it reduces thermal spalling, that is, the breaking of a material under high temperature conditions, and cracking and peeling off like this will be very much reduced. So these are the advantages and disadvantages of high porosity refractories. The next property of refractories is thermal spalling. It is the property of breaking, cracking and peeling of the refractory at high temperature. When it is subjected to heat, then it will expand, and when it is cooled, it will contract, and as a result of that, these can take place. There is breaking, cracking and peeling of the material can take place. A good refractory should have a very good resistance to thermal spalling, that they should not undergo any such crackings and peeling off. Now, thermal spalling is due to two reasons. The first reason is, when there is a rapid change in temperature, then an uneven expansion and contraction can take place. That is, an uneven stress and strain will lead to breaking, cracking, etc. Second is slag penetration. That is, in metallurgical operations, what happens is that we get slag, that is, all the unwanted materials will form a thick liquid, and these can bring about various variation in coefficient of expansion of the material. Then this will lead to thermal spalling. Thermal spalling can be decreased by three methods. One, by using high porosity refractories having low coefficient of expansion, that is, the change in size, that is, when they are heated and cooled, the expansion contraction will not be much, and thereby the thermal spalling can be reduced. And they must be also good conductors of heat, that is, they should have very good thermal conductivity. Second, by avoiding sudden change of temperature. This thermal spalling takes place primarily due to rapid change in temperature, so that can be avoided or can be reduced. And third, the furnace design can be modified in such a way the change in temperature is not much, or there is no sudden change in temperature. So these are the three methods by which thermal spalling can be decreased. The fifth property of refractories is dimensional stability. Now, refractory is subject to heat. It will expand in volume. Now, if a refractory shows greater resistance to any volume change, when it is exposed to very high temperature over a prolonged time, then it is a good refractory. Now, the heat can cause two types of changes. There is dimensional changes. First one is reversible, second one is irreversible. Reversible dimensional changes are changes that can be reversed. When there is an uniform expansion in volume and contraction, then that is the reversible dimensional change. A good refractory should be reversible. Second is irreversible dimensional change. This results in contraction of the material or expansion of the material when it is subjected to high temperature over a prolonged time.